We have previously explored the graph of a logistic function. And some of the things that we noticed in that graph is that initially the growth is rapid, nearly exponential. This would be true of the concave up portion. The inflection point represents the time of most rapid growth, and we talked about those superlatives, fastest growth, steepest slope. That is all at the point of inflection. After the point of inflection, so this was talking about the concave down portion of the graph, the growth rate declines. So it's still increasing, but at a decreasing rate. And because of this, the function has a limiting value, and a synonym for that limiting value is called carrying capacity. So as you're working with application problems, some problems will ask you for the limiting value, others will ask you for the carrying capacity. They are one and the same. This next bullet point has a really important mathematical relationship for us, and that is that the point of inflection, so the point of inflection, occurs at half the carrying capacity. So this really helps us with the math of finding either one. So if we know the carrying capacity, and then we can find the point of inflection by dividing it by 2, or vice versa. If we go back and look at our previous problem, we see this to be the case. So in our previous problem, our carrying capacity, or limiting value here, was 1, and our point of inflection was 0.5. And so we can see that if you just take that 1 and divide it in half, you have the point of inflection, or if you take the point of inflection times 2, you have the limiting value. And so they always have that relationship between those values. Now, you will notice here that it's between the y value. It does not give us the x coordinate, and we'll have to work at finding that, and we can use our graphing calculator to help on that. So back to our list of key things that we have here. The last, before I go on, the point of inflection can also be referred to as the optimum yield. And so in harvested populations, things that are growing to like shrimp and fish and those sorts of things, it's important to harvest them at that point of inflection because the population is reproducing very quickly at that level, and so it will not die out. If you wait until it's at the peak, at the carrying capacity, the population is not really growing anymore, and so if they harvest at that point, the population will not reproduce. And so this optimum yield is the idea of the point of inflection. So again, based on the context, some problems are going to ask you about optimum yield, and they're just asking you about point of inflection. So some of the things that this describes, it describes growth, and specifically percentage growth when there is a limiting factor. So when I'm reading word problems, the word problems start out sounding like exponential problems because exponential has that percentage growth, and that's how the beginning is connected. But then the problem introduces a limiting factor, and so that's what switches it from an exponential problem to a logistic problem. Some of the things that really impact healthcare are the spread of new technology. So in new technology, you have those people that initially trial the technology and they're right away adopting that technology. So I always think of the iPhone. So the new iPhone comes out, it's expensive, but slowly as the price goes down, more and more people get it. And then it's like everybody switches to it. And then you have those late adopters. So they're getting it like slowly on the discount. And then it kind of really just levels off with the people getting that particular iPhone because there's another one. But this spread of that technology is this logistic curve, but this happens in healthcare too. And so we all switch to a new technology, especially in the health sciences, and then that becomes the norm and pretty much everybody has it, and then something else comes out, or a new procedure. The other thing that's really connected to healthcare is the spread of the virus. So this is if you look at total cases. If you look at just new cases, you get the waves that we have seen with COVID over and over again. But if you look at total cases, so when COVID started back in 2020, there's just a few, and this is barely a blip on the radar. And then it spreads like crazy. And so everybody gets it. And then this happens every single year with the flu. So it's like a couple cases pop up in October. People get their flu shots to try to protect against it. But we get into that December, January, and just it's spreading like crazy. And then we get into the spring, so the March, April, and it starts to level off. And that season of flu is like done. So it doesn't continue to grow. It has a limiting value. And so lots of viruses are this way. Many of them have a seasonality to them, and as COVID was new, we had this like perfect logistic curve, and then it mutated, and it does like a whole different thing. And so it's a very complicated curve at this point of what's going on, because instead of having a limiting value of everybody can only get COVID once, we now know that people can get it more than once, which makes it even more complicated. But we are still seeing this logistic curve show up with the seasonal flu every single year. We see it show up with like Ebola outbreaks, with monkeypox outbreaks that's been happening. Lots of different places you see this logistic curve with the spread of a virus. So looking at the formula, the formula is up here in the top right, and key thing is down here at the very bottom. You do not need to memorize this slide. So you're just looking to understand, you're looking to do your problems with this in front of you. It will be given to you on any quiz or test. So in this formula, if you're making the formula or if you're looking at a formula to answer questions, this K up here is the limiting value. So that can save you a ton of time, because you don't have to scroll in the table of your calculator to find the limiting value if you know the formula. If you know the formula, it's given to you, right? So then that is a huge help in finding the point of inflection, because the point of inflection has as its y value, so the point of inflection has an ordered pair, and the way you get this y value for that number in the point of inflection is you take the k over 2. And so that's what this little formula is telling you. The point of inflection is that number is k divided by 2. The reason why they use the n there instead of saying it's the y value is because when we look at the logistic formula, n is the number of items. So the n, which is truly behaving as the y value, is k over 2. The notation n of 0, this whole notation, is the starting population. Now, in linear, y equals mx plus b, we put the starting number in for b. In NPAT, we put the starting amount in for p. In logistic, we do not put the starting amount in the formula. We use the starting amount to figure out this constant b, and b is the one that goes in the formula. So what we do is we have to figure out this number b, and so if we look at this, the way we figure out b is you take the limiting value, you divide it by the start, and then you subtract 1. Now, in your homework, you're going to do a lot of problems that have you work within this formula. So sometimes they're going to give you b, and so they might tell you b is 5. And they might tell you the limit is 20. And now you're supposed to figure out what was the start. And so all three of these are interrelated with this formula. So I can take things and put them into the formula. So if b was 5, I put that in. K is 20, so I'll put that in. Instead of n over 0, or n of 0, that whole notation, I'll just put an x there. I don't know that. And then I do have this minus 1. So if I think about how does this work? Well, the way that I would solve this out is I first have to add 1 to both sides. So plus 1 on both sides. So that gives me 6 equals 20 over x. And then this can be tricky to solve because our x is in the denominator. So the easiest way to do this is to put as a 6 over 1, have a fraction, and use the cross product. So 6x equals 20. And then if I divide by 6 on both sides, I get x equals 18 would be perfect, but it's not 18, it's 20. So 20 divided by 6, I'm going to my calculator, 3 1/3. So 3.33. So you might have to do some algebra. You, again, don't have to memorize anything on this slide, so you don't have to memorize the formula, but you do have to be able to use it. So understanding that k is the limit and 0 is the start. And so for this one, this would have started out with 3.33, or about 3 1/3 of that item. Now we have this next section, and so R is called the intrinsic exponential growth rate. So if there had been no limit, this would have turned out being an exponential function. And so instead of the p, you see the n is 0. That would have been the start. So that would have been the p, like in NPAT. But then instead of having a percentage here, we use this e, and we've talked about e different times. So e is this base for continuous growth. And so like a virus is continually spreading, and so this base of e is used. And so the exponent then is this r and t. But none of that is going to be happening because there's this limiting factor. So this would only happen if there were no limiting factors. But this is helpful in figuring out what number to put in for r into the formula. So we have 3 formulas. Again, you do not have to memorize them, but they are very important. We're going to end up using them a lot, and they're in these 3 bullet points. So the first one is that A can be found by taking e to the r. So if you have a formula and r is given, notice that it's a sign change, because up here in the formula, this is negative, but down here, this one is positive. But you can take e to the r power, and that gives you a. Now, a is the base of the MPAT. So a is 1 plus the percent of the decimal. And if you happen to know the percent of the decimal, you can get a and then take the natural log of it and get back to r. So we will do some problems in our lecture portion and in our homework that relate these 3 formulas together, the relationships that we have here between a and